Thank you. So hello, everyone. My name is Abhishek. And then today I want to talk about these two things. So the first is two stories. So these are non-fiction stories about research software development. So the first story is about a manual annotation software that is up and running anywhere in less than a minute. And then the second story is about a visual image search engine that does not require technical expertise to either install or to use. So these are the two stories that I want to present first. And then in the second half of the talk, I want to talk about a research that I've been doing recently, which helps one learn the art of writing code and documentation that is easy to understand and then that is easy to maintain. So there are two parts of this talk. So let us go on to the first part, which is a set of stories. So first story is about a manual annotation tool. So in 2015, I want to tell you a bit of what was the state of a manual annotation tool back in 2015. So a manual annotation tool is a software that allows a human to draw regions in an image and then define those regions using keywords, as you can see on the right-hand side in this animation. In 2015, our lab was forging new collaboration with Department of Humanities, and then they were doing a computer vision project where humanities students had to annotate a set of images. And basically, a manual annotation software is a way for humans to transfer their knowledge about the world to machines. That is how I see it. So a human says, this is a swan, and that's what the machine learns, how a swan looks like. So here is an anecdote from 2015. So a DPhil student in our lab, so you can imagine that DPhil student was an expert in many fields. So that DPhil student spent several hours of his very precious time in installing a manual annotation software in a laptop of another student from Humanities, several hours. And it was a very frustrating experience, both for the student as well as for this DPhil student who was trying to install it. I think this is a waste of time of highly skilled people who can do lots of other things that are more beneficial to everyone. So we knew that we needed a manual annotation tool that is up and running in less than a minute, that doesn't require any expertise. And then it should be running anywhere. So when I say anywhere, it means on any platform. So it could be a Mac or a Linux or a Windows, and any place. So imagine you are traveling on a train and you want to do some annotation. So it should be able to work there as well, where there may not be an internet connection. So those are were our requirements at that time. So I started my job. This was my first assignment. So I came up with this 34 lines of code that could do the full annotation in a web browser. So now for those of you who do not know about JavaScript, HTML, and CSS, I give a quick tour of what this code is about. So these two lines here, so one of them shows the image that you want to annotate, and then the other one draws a transparent canvas on top of that image so that it could draw the boxes that you are drawing on the image. These lines here, these are the CSS that makes sure that the canvas is on top of the image so that you have an illusion that you are drawing on top of the image, whereas actually you are drawing on the canvas. These two lines, these ensure that the image and the canvas are of same size. And then finally, this part of the code records your mouse clicks, and then it stores those clicks to quantify the boxes that you have drawn. So that's it. With these 34 lines of code, you have a manual annotation tool that can run anywhere that supports a web browser. So that was in 2016. So we built this tool and gave it to the students, and then they said, this is amazing. So this was in 2016. So my first assignment felt as if it was complete. So problem solved. Should we pack up? We told ourselves that it's not yet time to pack up. Let it grow organically. This tool seems to have a lot of potential. So let it grow. So we fulfilled the requirements of few humanities students in our university. What about other researchers in the university? What about other departments? So we found that other departments are also keen to use such tools. So a DPhil student used this tool to annotate a piece of art. And then as a part of her DPhil thesis, she submitted not only the annotations, but also this tool that allowed her to annotate. So that was used in history of art, research in geography and environment, they used it, and many other departments started to use it. We asked ourselves, what about other researchers elsewhere in the world? And then soon we saw there were many other researchers all over the world who were finding this tool very useful, mostly because it was very simple to use. It was not complicated at all. After some time, we saw that you really don't need to be a researcher in order to use this tool. You could be a photographer who is interested in doing something, some annotations on their photograph, or you could be an employee somewhere in a country who is trying to annotate a highly classified document. So this employee wrote to me saying, when I use your tool, can you guarantee me that these images do not go to your servers and it stays in my computer? And I told him, yes, it doesn't go anywhere. And then he started using. We saw that there were many other people that we never thought would use it. They were using it quite easily. And soon thereafter, we saw many companies started to use this tool in their commercial products. And then all of these companies, they're using it, either by building a more complex tool on top of it, or just using it as it was. So we saw this tool grow organically over several years. So this was the state of the tool in 2016. This is how it grew in 2017, where we supported polygon regions. In 2018, it had more features, so it could define attributes as well as more complex sets of relationship between them. And it did grow organically. So here are some examples of how this tool is being used. So in humanities, there are lots of images, and then the researchers, they see a grid view of images and they annotate it. Many researchers are using it to annotate insects in videos. It now also supports annotating subtitles. And we have also seen this tool being used in a lot of medical imaging, mostly because this tool is offline, and medical images have quite a strict requirement on how they can not be put online because of privacy issues. So clinicians, not only in the UK, but all over the world, they use it because they trust it, that the images will not go anywhere else. Most recently, anthropologists have started to use it. They want to study the behavior of chimpanzees. And then they have videos of chimpanzees in the wild. And then they are using this tool to annotate not only their social behavior, but their actions as well. So for example, this annotation shows here that the chimpanzees were cracking a nut in this segment of the video. And then in this segment, they were using a tool for certain task. So they are embedding this human knowledge into these videos, which are then used by computer vision algorithms to learn how to classify their behavior. Now looking back, we can see the benefits of organic growth. So our users, they asked us a lot of questions. They reported a lot of issues initially, a lot of bugs reports we received. And then they also often not only requested for features, but they also contributed code to improve the software. So this helped nurture a very vibrant community of open source users. So because we only had limited resources to develop this tool, this was very useful to us. We could do more because we had a community around us. Over time, our software became more stable as more people tested it all over the world and then sent us feedback. We learned about many new use cases that we had never imagined about. For example, people using this tool to annotate high tension wires because they want to build a tool to automatically inspect these tension wires and then use machine learning tools to do that task. So I often ask myself, what would have happened if I had backed up at that time? In terms of numbers, we would have missed around more than 790 citations. And then these are citations from mostly non-engineering disciplines. So medicine, anthropology, humanities, literature, all these non-engineering disciplines. And then we know that our software has been used more than 6 million times since it was released in 2017. We receive a lot of feedback. Most of them are positive feedback, encouragement, as well as questions. So this helps us in a lot of ways. We get feedback for free. A lot of people test our software for free and give us feedback, also contribute code. And then we know which companies are using because they tell us that we are using your tools. So that was the first story about nano annotation tool. Now let us move on to the second story about a visual image search engine that is so simple to use that anybody can use it. So the story goes like this. In 2014, our lab had a remarkable software. This software could instantly search millions of images. So in an instant, you could search 1 million images. This capability was used in one of the research projects to understand these broadside ballads that were printed a long time ago. So this software was used in this project. This is some screenshots from that project. So you have a set of images. The user defines a query reason on what they want to search, and then they press the search button, and they come up with a set of results, which shows where else that illustration appears in that data set. And this search is based on the visual content, and it can match even when there are some occlusions or some defects in the image. So this was a remarkable piece of software, and then this revealed a potential for the software, because now you had a bridge between the humanities and the computer vision community, and then it was powering up a research that was not seen before. So we decided to release this software as an open source project so that others could also use it and benefit from it. The software had excellent performance, so it was instantaneous search. And then this was like a personal search engine. So if you had a private collection of, say, 10,000 images, you don't need to upload it to Google Search or Google Photos to make it searchable. You could still keep it in your laptop, private, install this software, and use it as your personal search engine without giving away your photos to any other service provider. So it had a lot of unique selling points, and we thought this would be a great hit if we released it. So we started to prepare it for release. We built a web browser-based user interface, which looked like this. And as we developed more resources to it, soon we ran out of patience. We had limited number of developers who could work on it. So we didn't invest the amount of time that was required to port it to all 3 platforms. So we wanted users in all these three platforms to be able to use it. And most of our users, they are from Windows and then Mac OS platforms. So that was a requirement. Because we didn't invest a lot of time, we didn't have that much of resources, we decided to go a shorter route. So we made this tool as a Docker image. So Docker is a software that allows you to run tools on a virtual environment. So we made a Docker image and then put it out, thinking that our users would be able to download this Docker image, run this Docker container, and then run our software as well. After we released it and after some time, we started to notice that we were the only users of this tool. Nobody else was using it. So most of the deployments of this tool required our involvement, our technical expertise in order to make it usable. So anybody who wanted to use it, they had to contact us in order to resolve their technical issues. We learned quite a lot of lessons during that time. It was quite frustrating that this wonderful piece of software was not being used to its full potential. So what we learned is installing Docker, pulling images, mapping volumes. These are non-trivial tasks. And then as a technical person, although I see these are quite simple tasks, for a non-technical person, for example, a humanities student who is not aware of these tools, for them this is a big constraint. They don't want to get involved in these complex tasks. Our software was also frustrating in many aspects of user experience. So the software froze in the middle of a long computation. So you had to redo again everything from start. When it broke, you had to do a lot of tweaks, and that required our involvement. Many large institutions, they were impressed with our tool and then its features, but they were quite fearful to commit to it because they were not sure if they would be able to get the required support if they used it. For example, museums, they were not sure if they want to commit to this software. So we failed. Such a remarkable software deserved something better. And then we failed. And then we decided to do better at that time. So this was in 2019. Now we no longer assume that our users had the time and expertise to install a complex piece of software. We gave this as the benchmark for ourselves. So our tools should be ready in less than a minute. We also accepted that we didn't know a lot of things about our users. Many times we had ideas for lots of great features, and we dumped everything into our software. What we learned is if adding a feature complicates the installation process or the usability of the tool, we should not do it. We should not include that feature in the software. As an alternative, if the feature had to go into the software, it could go into an advanced mode, which would be used by more technical people, like command line interface. So that is what we learned. So during 2020 and 21, we pursued these two goals. The first was to simplify the installation process, and the second was to improve its stability. So how should you simplify the installation process? In our software, there were multiple layers. So there was a web browser front end, there was a Python front end, and then a C++ backend. So this complicated quite a lot of the installation process. So we removed one of these layers. So we removed this Python layer and then simplified the design to some extent. And we rewrote a lot of code so that we completely removed Python dependency. Not because Python is something bad, but because we wanted to have a simpler install experience. So if it is just C++, it's much simpler to ship. And we also built installers that were native to that platform. So on Windows, you have a certain type of installer, which looks familiar to a Windows user, like this. On a Mac platform, you have a different type of installer where you click and drag the application to the applications folder. So we used a CMake to build a native installer for each platform. The second point which we worked on was to improve the stability of our software. So every bug report from our users contributed to improving the stability of the software. So we treated every bug report as a blessing. We believe that this bug report, once we address it, our software will be more stable. And then that was the positive attitude that we started looking at the bug reports. And then we didn't have any tests. So we had 0 tests. Now, I have to admit that I find it, so when I have to do a lot of work, and then if writing tests is one of the tasks, I would put it lower down my to-do list with lower priority. That had been my attitude towards tests. So it consumed a lot of time that could be used somewhere else. So therefore, we didn't have any tests. And then whenever this thought of writing tests came, it always felt like insurmountable set of goals. It was so huge that you could never write tests to fully test the software. Therefore, you never started writing tests. We told ourselves that there is no pressure to write tests for all parts of the software. You do not need to test every aspect of the software. You start with something that is the most important part of the software. So if it is a visual search engine, it should be able to search images, right? That's the core functionality. So you take 100 images, you test using one of the query images and see if it returns the 10 images that you want it to return. So that's the most fundamental task that the software has to solve. And you just write tests for that. That's it. Don't worry about testing every other aspect of the software. So what we did was, right now we only have one test, which is based on a smaller subset of 100 images. And this test does exactly that. What I said right now is that it gives it one query image and checks whether the software is able to retrieve the 10 images that it expects it to. And then this test that we have right now, it is improving as we go on, but it gives us some confidence, not full confidence, but at least some confidence that when we give this out to our users, at least it will be able to search the images. So that was about the test. I have to admit that I have learned this in recent times. 3 years ago, I was not very fond of writing tests. I thought it as a drain on my time. But now I have slowly realized that the value of these, and I'm allocating some time to it. Not a lot, but some time. The second is we are using our online demo. So we have a lot of online demo that you can go right now to our website and try it, all these visual search engines. So after the talk, I'll share these slides. So you could click on those links and go to the online demo and do the visual search on your own. You could upload your personal images as well and then check if that image exists in the dataset. So those online demo, we had been using it just to showcase our software in the past. Now we use it as a way to improve our software as well. So we noticed that a lot of our users managed to crash our software in many ways that we cannot think of. So they upload certain images that are sometimes not well formed, JPEG, and that crashes our software. So we decided to use these software crashes as a way to get new bug reports and then address those reports to make our software stable. So now we run our demo in a debugging mode, which means that whenever the software crashes, it dumps a log of where and why the software crashed, and then restarts itself. So the user doesn't see anything or feel anything. So when the software crashes, we receive a report, the online demo restarts itself. And then we look at the report. For example, this is a snapshot from one of those reports. So it's a segmentation fault. And then once we get this report, we try to debug it and then find a fix for it. This has helped us quite a lot to improve our software. Our demo are less unstable now. So if our demo crashed, say, once in a month, now they crash, say, once every 6 months. So it is getting more stable, but we really like when our users crash our software. That is a positive attitude that we have developed about software bug reports and crash. And this is a sample screenshot of what happens with the test. So every time we change something in our software, there are automated tests that test this software on all these 3 platforms. So it's a Debian Linux, Mac OS, and then Windows. And this test is based on, as I said, 100 images taken from a standard dataset. This dataset is called the Oxford Building Dataset, which contains around 5,000 images. But we only take a subset of 100 images because running on all those 5,000 images takes a long time. So this 10 images, it completes in less than 5 minutes. So we have selected this. And every time we make a change, this test goes through the software, provides a query image, and checks whether it gets back the set of results that it expects. And then when the performance is within a range of acceptable range that we expect it to have, then we say the test has passed. This has proved quite useful in assuring ourselves that every time we make a change, it is not breaking anything in the software. At least it is not breaking the most basic functionality of the software, which is to search the images. There are many other functionalities, like it can also group images based on visual content, but we are not testing that yet. We are only testing the basic functionality. In the future, we want to build more tests, but that has not yet been done. So if I have to summarize what we learned from our failure, this is it. So the first one is that someone has to spend time. It can be either your users who collectively spend countless of hours installing and setting up your software, or it can be you, the developer, who spend certain amount of time making this process frictionless and then quick. I think choosing from one of these 2 options is not difficult. And we have chosen this option. The second learning that we had is that it helps to design a software for the many, even when you know that only a few people will use your software. Now, the reason for that is because when you design for many people, this forces you to not expect too much from your users, and therefore simplify your design so that many people will be able to understand it. And then your users won't require technical expertise to use your software. And this is, the third one is also quite important for me personally. I've seen that when a lot of people use your software, you get more feedback. And if you have time to address those feedback, there is nothing stopping you from achieving stability and usability in your software. So these are the learnings from our failure. And now we are seeing a lot more independent users adopting our software. These are some of the examples, but there are many more. And this is a good sign for us. Now, these two stories are our true stories, and I have lived these two stories, and therefore I can tell you that being a character in these stories, so far I have summarized these as my learnings. So I make sure that my software tools are up and running in less than a minute. My research software should not only be built for researchers, but it should be built for many other people who may find it useful. I often ask myself, will a high school student be able to use my tools for their science project? And this helps me gain a lot of clarity in terms of design, in terms of many other aspects like documentation. And finally, the road to stability is decorated with bug reports. So when you receive bug reports, think of it as your ticket to a more stable software. That is the positive attitude that I have recently gained. And that helps me to improve the stability of my software. So I still have a second part of my talk remaining, but if you have any questions, you can ask me right now. If not, we can move to the second part and then ask all the questions at the end. Okay. So I'll move on to the next part if there are no questions. So in the second part, I want to talk about my recent research. Now, the goal of this research is to help learn ways to write software that are easier to understand and that are easier to maintain. And then I call this as a software resurrection. So let's see what it means. So this diagram summarizes what the concept is. So you start with a historical software release. You compile it in a modern platform, so in a modern laptop. If the software fails to compile in a modern platform, you develop a fix so that the compilation as well as test succeeds. So that is the testing phase. And if either of these two phases they fail, you have to develop a fix. And then the final stage is to write a critique based on your experiences of compiling and testing that software on a modern platform. Now, for this talk, I have selected this research software that I initially encountered during my MSc. So this is a research software by Nihab and colleagues, which was released in 2005. And this is a way to combine information from two different sources and then come up with a better geometry of an object. So the authors have released this code on their website, and then I tried to compile and test their software in my modern laptop. So I started with downloading the software and then compiling. But the compilation failed because it had some dependencies that were missing in my laptop. So I went on to find the dependencies. And then located one of them. So it's a library called CHOLMOD, and it's a part of another bigger library, and I located that. I tried to recompile again. It complained about another missing dependency, so I again compiled the other missing dependency, which is called trimess, which in turn depended on another dependency called OpenGL, which fortunately was available in my package manager, so I could easily install it. So after installing all these dependencies, now I again try to compile this software. So when I have resolved all the dependencies, I come across some more issues with the code. So I fix them as I encounter them. For example, by adding namespaces that were required. There were more errors that we encountered because compilers have become more strict in terms of what they tolerate. So I resolved all those errors, for example, by adding a const qualifier here, which is now required by compilers. Also, I added some namespaces, qualifiers there, just to make the compilers happy. Once the compilation was successful, it goes on to the linking stage, which implies that it is resolving all the symbols in the dependency library. So I encountered a lot of undefined reference errors. So after a lot of hit and try, I found that compiling the code using all these dependency libraries compiles the code successfully in a modern system. So I could run this software that was created 17 years ago. But I couldn't test this software because there were no tests provided with the code. So after all the hardware changes in the last 17 years and the software changes, I find it difficult to believe that the software is behaving exactly in the same way as the authors had intended when they released it in 2005. But fortunately, the authors have provided a detailed expected output of their commands, as well as the specifications of their command. So I run these commands, and I get the results. So it was, I felt quite excited to see that the code that was written 17 years ago was still able to run in the same ways as the authors have pointed out in their expected output, with just one difference. So in my output, it said that it removed 479 phases, whereas in the output that was presented by the authors, it said it removed 480. So there is a discrepancy of one phase here, and I don't know why. But I'm still convinced that this code should be fine to use, because in general it is working well, and it is producing the output that looks reasonably well. But there is no other way to verify whether it is doing what it should do. I also noticed that the code that took nearly 2.5 seconds in 2005 now runs in a lot less time without making any changes to the code. So it is all due to the changes in the hardware and software in the last 17 years. So that was a summary of compiling and testing a software that was released 17 years ago. Now let us quickly look at what we learned from this, doing all this. So this is what I feel is a critique of the software. So the first is, do you want to depend on a software? Now, from this exercise, what I learned is if a software A depends on another software B, it has implicitly accepted that its fate is tied to the other software that it depends on. This software, so Will, who is in the audience, he created a MATLAB version of the software in 2020 because he felt that the software was difficult to compile due to its dependencies. There could be, the goal could also be to learn what the software was doing. But based on what we experienced, we know that when the dependencies provide you with a lot of issues, most of the time it is quite frustrating, and then people just leave it and they move on to make their own implementation of the software. So a wise developer has to look not only at benefits of a dependency, which is mostly obvious, but also at the cost of depending on the software. And then weigh these benefits and cost with some impartiality. So that was one of the lessons I learned. So choose my dependencies more carefully. The second is one cannot always rely on compilers to be nice. So if a compiler is lenient right now on certain aspects of your code, by just issuing a warning to you, it doesn't mean that in the future it will not be an error. So compilers are known to be stricter over time, and whatever is a warning right now, it may turn into an error into the future, say after 20 years. And at that time, a user from the future may not be able to understand what that error means, and therefore may give up on reusing your software. So one has to make sure that if a compiler complains about something, one heeds to that warning and addresses it in certain ways. Third, which is about test, is that test builds trust. So most of us know that test is used to test the functionality of the software, but there is another value of having a test, that it builds trust in the software. So this software, which was written 17 years ago, when I try it now in my computer, I have no other way to verify except the output that was reported by the authors. So it is difficult to build trust on the software because there is no way to verify what it is doing unless you are an expert in understanding the code. So if you do not have time to write tests, it is always a good idea to inform the users about what you can expect from the software when it is running, like the authors have done here. And it is also a good idea to provide some sample input and output so that users can cross-check between them. So I was able to do this because the authors have provided this output here. Fourth is that from this exercise, what I learned is that your code will run faster in a future hardware, even if you don't do anything to it. So as we saw that the code that was released 17 years ago, it ran 45 times faster in a modern machine without any change. So all of those changes all of those gain were due to the hardware as well as the software, the libraries that it depended on. It is not always a good idea to optimize your code to gain few cycles because it is difficult to understand such code, and it is also more difficult to maintain it. So if you can describe a computation in, say, 3 lines of code, then I feel that is much more valuable than optimizing it such that it's just one line of code to save some CPU cycles. When I was running this code, I also missed a readme.txt file, which is not there in the distribution. So I missed that file, but a lot of excellent explanations were provided in the reference manual and the examples, which are available as a website. So it is a good idea to include a text file that contains some basic documentation of what the code is about and then how to run the code in the code itself or in the folders that you supply with the code. So I feel this is a remarkable piece of code because even after 17 years and then some fixing, it is still able to run in such a optimized way and produce such results that are similar to what the authors had reported. So I think this is a remarkable piece of code that is very valuable for learning as well. And there can be many more learning experiences based on how you see all this exercise. So there are many more exercise there on this website here. And then this is an exercise that I feel is a way for me to learn how to write code and documentation that is easier for others to understand. And then that is easier to maintain in a long time scale of let's say 10 or 20 years. So with that, I come to the end of this presentation. So if you have any questions, please let me know.
Thank you very much, Abhishek. Let's give an online and in the room round of applause.
Thank you.
Right. If anyone's got a question, just unmute, or if you're in the room, shout.
Okay. Maybe then
I'll go with something. So I guess you're in a very well-resourced research group which can afford to employ a research software engineer to help with this stuff. Like as researchers, we would effectively have to make the choice between like all of the good practices that you've described take time.
Yes. Yes.
And that time will be taken away from basically doing more research, working on other projects. So we'd have to make the decision to kind of put time into software engineering over doing more research. I guess the question is, do you think we should just do that? So do less research, but do it better in a more reproducible way?
Yeah. And that's a wonderful question. So even when we have resources to afford, let's say, 3 research software engineers, even we find it difficult to allocate the amount of time that is needed to follow these best practices. So as I said, even we don't have the time to write all the tests. But in the past, what I've realized is that instead of achieving the perfection where you follow all the best practices, you do all the things that are advised by people, instead of trying to achieve that, it's always more feasible to just do one thing good instead of doing everything. So instead of having, say, 100 tests, it's already great to have just one test. Instead of having a documentation that is so extensive that a book could be printed on it, one could have a simple readme.txt file which explains just the basic things. How do you compile this software? In just few lines. How do you run this software? And what is the expected output? So the benefits of these are immense. As I showed you, the code that was released in 2005, I can still communicate with it. I can still use it. I can still compile it because the authors have provided the source code, the sample data, the MES files, as well as the normal maps, as well as an excellent documentation describing what command parameters to use and what to expect from that command. So even doing simple things goes a long way. And I completely agree with you that it is really difficult to follow all these things. I don't follow. Therefore, I admit that I don't have lots of times to write all the tests, and I don't do it. I try to do the best that we can afford based on the time and the number of tools we have to support. So do as best as you can. That would be my advice.
Okay. I'm just going to stop the recording.